Okay, very good morning, people. Um, Started the recording. Anything else to be done? No. So, last time we have been speaking about the theoretical type of wind, which people thought for a considerable period that it is a theoretical wind, that is geostrophic wind. And following the curved path, it could be called as the gradient wind also. However, there came up something during the Second World War which led to the identification of a peculiar type of wind, which was named after again a peculiar phenomena. What used to happen is that when the American um, bombers used to travel towards Japan, they found that in a particular direction, okay, particularly when they were moving towards the east, when they were moving towards the east, the speed of the planes used to be faster, and when they were going towards the west, the speed of the planes were slower. As a consequence, you'll see that when they used to travel towards the east, they used to fly in a particular direction. But the same direction used to give them a significant amount of resistance, and that is why they used to fly over that particular issue. Because of this, they found, and of course they came back and they reported this to various scientists that we are experiencing these things happening in the upper layers of the atmosphere. And while they were reporting this, of course, scientists started studying about what actually should have been the thing that is happening with all these things, and eventually they found out that there is a type of wind which is blowing. Because these were reported by the jet pilots who were flying in that particular range, they were called as jet streams. And today we are going to do a few things about jet streams as such. But as I said, that we are around a very interesting and a very important part of climatology, which relates to many things. And every time you come back to knowing this particular thing, what happens is you tend to understand it in a different way. You understand it in a better way as such, and that is why you'll see that I would again take you back a bit back, and we'll restart a few things, and accordingly, gradually we'll come down to jet streams, and I'm sure you would understand it better as such. So I will start with what I will start with this. This is again, just a moment. This is a diagram which I found, which I have taken up actually from the Lutens and Turbuck book. And yeah, okay. So this is the one from the book Lutens and Turbuck. And I found that these were the best of the diagrams you could find as far as winds were concerned. And I would rather say circulation of the atmosphere. Sorry. Circulation of the atmosphere is concerned. Of course, they should have been, this one is the earlier diagram, so this should have been here and this should have been here. But given the importance, this is more important, and that's why I've kept it aside. Remember that first of the cycles, global circulation on a non-rotating Earth, okay, you see non-rotating Earth, was that you have warmer air here, so you're going to have low pressure here. You have colder air here, so you're going to have high pressure here. So what happens is it's a cycle like this. Okay, so a convective cell happens in both the hemispheres, of course. In 3 dimension, it looks like this. Remember that along the equator, the thickness is going to be more. Near the poles, the thickness is going to be short. Okay, I purposely keep on repeating this basically to give us a fair idea. Okay, बऱ्याच वेळेस असं होतं की काही गोष्टी आपण गोंधळामध्ये समजून घ्यायच्या राहून जातात आणि मुद्दाम त्या रिपीट केल्यामुळे काही गोष्टी ज्या मिस झालेल्या असतात त्याचं कनेक्शन होतं व्यवस्थित आणि आपल्याला ते समजतं देखील. Then coming to the three-celled model, okay, or it is also called as the Maridonial model. Maridonial. Okay, you know that along the equator you're going to have low pressure, mid latitudes you're going to have high pressure. Here you're going to have low pressure again, and at the poles you're going to have the high pressure. This is cell number one. Okay, one thing keep in mind, you'll see that the thickness of the cell goes on decreasing towards the northern end of the cell in the northern hemisphere and southern end of the cell in the southern hemisphere. The thickness here is different, thickness here is different, thickness here is different, thickness here is different, and so on and so forth. Okay, cell number one, the Hadley cell, cell number two, the Ferrel cell, cell number three, the polar cell as such. You'll see that you have clouds here. Okay, low pressure and clouds are related to each other. So low pressure and rain is also related to each other. High pressure and dryness. Okay, this is moist. Okay, this is again going to be moist here, and this is going to be dry here as such. You're going to have alternating dry and moist pressure belts as such. Now between the pressure belts, we have seen that ती आपण त्या दिवशी ती रेस लावली सगळ्यांची आणि आपण पाहिलं की ते कसं कोणी पुढे जातंय कोण मागे पडतंय. तर इथे मागे पडणारे जे हे आहे that leads to easterlies, okay, which are also called as the trade winds. Okay, they are equatorial easterlies you are called as. And then you'll see that हे पुढे पडणारे जे particles आहेत that leads to westerlies आणि हे rebound theory जे आपण म्हटलं, that rebound theory leads to formation of polar easterlies once again as such. This is of course, remember, this is idealized. Okay, याच्यामध्ये मागे land surfaces, water surfaces, all are going to make a difference. And we have seen that this difference is quite prominent as far as the northern hemisphere is concerned, because you have a lot of land in the northern hemisphere. But in the southern hemisphere, particularly beyond 30 degrees latitude, you'll see that the pressure belts are more or less prominent all throughout. That's basically because of the fact that you have more water in the southern hemisphere. As okay, with this, let's move ahead. We saw that we have a low pressure somewhere, we have high pressure somewhere. There is going to be a gradient. This gradient, okay, I showed it to you the other day in a different format. This is again in a different format as such. You have a high pressure here, you have a low pressure here. You can see the pressure value, okay, from 1116, that's here, to as low as 992. Okay, you'll see that if you see the difference, okay, the difference between these two is 4, the difference between these two is 4, 4, 4, 4, 4. What is happening is the distance between the two isobars is decreasing. Okay, so because the distance is more but the value is same, only because the distance is more, you have a weak pressure gradient. On the other hand, towards this side, you have the lesser distance, and that's why you have a steep pressure gradient. Okay, so and this side it's going to be like somewhat like this. Towards this side, it could be gentle, somewhat like this. As such. Isobars are lines connecting. These are isobars. Okay, these lines, lines connecting places of equal atmospheric pressure. The spacing between isobars, e.g. spacing magashi mi म्हटलं. Okay, the spacing between the isobars is the amount of pressure that change occur in a given distance, called the pressure gradient force. Okay, we use this value, pressure gradient force. Closely spaced isobars indicate a strong pressure gradient and high speed winds. Okay, so here the wind speed is going to be high. Okay, here the wind speed may be gentle, may be low. Okay, so this is what happens. Okay, as far as pressure gradient is concerned. I hope this confirms your impression about what pressure gradient is. Then we come back to another interesting thing that I don't know where, I think I found it in Luton's as such, but this is something that we have done the other day. This is something that we have done the other way. This is something that I have added. Okay, you'll see that this is the lifespan of the wind system. Days to week, hours to days, minutes to hours, seconds to minutes as such. Okay, now these are wind gusts, microburst, dust devils. Dust devils म्हणजे ते छोटंसं चक्रीवादळ असतं. आपल्याला लहानपणी सांगितलं जायचं की त्याच्यामध्ये मीठ टाकलं की तुम्हाला भूत दिसतं. डस्ट डेव्हिल्स म्हणतात त्याला. Okay, this is micro scale at a very, very, very zoom in stage as such. This is the mesoscale. Okay, and of course, this is the macro scale. Now the perception changes. You'll see that here thunderstorms and tornadoes and local winds. Okay, you'll see that as far as these initial ones are concerned, they exist for me clear करतोय उगाचच घाणेरडा गोंधळ नको इथे. Okay, याचे कलर्स पाहायचे तुम्ही. Okay, so this color matches here. So wind gust, microburst, आपण एक झुळूक येऊन जाते. Okay, so dust devils, all of these are from a few seconds to minutes as such. You will see that these occur for a few minutes to at times a few hours as such. And then this is from a few hours to days at times as such. Then days to weeks madhe you have these mid latitude cyclones and then waves in the westerlies and trade winds as such. Okay, this is planetary scale and that's why they are going to be called as global winds. Okay, this is synoptic weather map scale. Okay, this scale is macro, this is meso, okay, and this is micro. Okay, now remember one thing, that we spoke about large scale maps and we have spoken about small scale maps. Okay, large scale is close up. Okay, small scale is zoom out. Now if you compare this to this micro meso macro scale, okay, actually this is going to be macro. हे इथे गोंधळ होतो लोकांचा म्हणून मी हे दाखवतोय. आणि लार्ज स्केल इज मायक्रो स्केल. मायक्रोस्कोप घेऊन तुम्ही पाहता तेव्हा तुम्हाला जास्त डिटेल्स दिसतात. जॉग्राफिकली दे आर कॉल्ड एज लार्ज स्केल. ओके, अँड दिस इज द मायक्रो. ओके, लार्ज आणि स्मॉल आणि मायक्रो आणि मॅक्रो याचा एक्झॅक्टली ऑपोजिट रेफरन्स आहे, लक्षात घ्या. ओके, सो वर्ल्ड मॅप which is small scale in geography is going to be macro scale. But a city map, which is large scale in geography, is micro scale. Okay, and these are the three scales of atmospheric motions here. Gusts, okay, that's the A part. This is A. Okay, B is this, and C is this as such. So that is satellite image of an hurricane in C as such. So that is what we have to understand as far as this is concerned. Hope this gives you a broader picture as to what actually tends to happen with this as such. Something again, I think I did not come up with proper pictures last time, and so I again thought that I should be adjusting the photographs from Luton's to give you a better picture of what could be called as diurnal winds. Okay, you'll see that the top one, the A part, this part, during the daylight hours, daylight sun ahe ikde. Okay, cool and dense air, cooler and denser air over the waters. Okay, this is cooler. This moves this way onto the land, generating sea breeze. This is going to be called as sea breeze. Okay, so you're going to have low pressure here, you have high pressure here. Here, this becomes high pressure, this becomes low pressure, and so the convective cell tends to happen all the time that you have the sun in the sky. During the night time, when the moon comes up, you're going to have opposite conditions. The night and the land cool. At night, the land cools more rapidly, okay, and than the sea, and thus you're going to have the sea remains warm, that's low pressure, and this is going to be cooler, high pressure. The movement and the convectional cycle or cell completes itself. As far as the mountain and valley breeze are concerned, during daytime, what is happening during daytime? Okay, the air along the mountain slopes, this, okay, warms up and it moves along the mountain slopes this way, and the heavier air keeps sinking down in this particular direction. Something opposite happens after sunset. The cooler air tends to blow along the mountain slopes and it pushes. Okay, this is thermal. Remember, this is dynamic. Okay, the cold air, which is denser, it pushes up things all the way up. Okay, so and of course we have seen this in inversion of temperature also. Okay, so त्याच गोष्टी फक्त वेगवेगळ्या अँगलने आपण पाहतोय. Let's move ahead. Okay, you'll see that when air is blowing on the surface, okay, there is going to be a friction, and this leads to the of course you'll see that there are going to be undulations, and because of that, okay, you'll see that the friction is going to be of various ways, and air takes various shapes, or rather directions. The directions do change, but as you go up and up, you'll see that the impact of the friction layer, or the friction of the surface, it goes on decreasing. Okay, it becomes very, what is making it turn literally 90 degrees here, okay, tends to turn into just a few degrees, 10 degrees, 20 degrees, 30 degrees only, okay, as it goes up. And in fact, as you go further up, okay, you'll find that it goes in single digits. The variations would go in, say, at the max it could be 9 degrees, or it could be 1 degree, 2 degree, and at that particular scale this hardly matters, I would rather say. And in fact, as at a particular height, the other day we are speaking about the geostrophic winds. Okay, there is zero frictional force. As a consequence, it moves directly in the direction of the low pressure from high pressure, and it could be and of course there is no deflection in that as such. Okay, and we have seen how then the Coriolis force comes into picture. Because of the Coriolis force, it keeps on deflecting. The Coriolis force plus the frictional force, it leads to what we have seen here as spirals, which tend to develop when the winds tend to blow as such. Okay, all this we have done, so I'm not going into the details as such. Once again, understanding geostrophic winds is quite simple. Okay, you'll see that you have high pressure, sorry, you have high pressure at one end and low pressure at one end. The pressure gradient force is going to be this way, and of course the Coriolis force is going to be in a particular way, and then all of this is going to be into say the frictional force is in this way. You will see the here असल्यामुळे, if you concentrate on this diagram, now it is much clear that the PGF is in one direction, the Coriolis force is pulling it in other direction. It's not exactly equal, and त्याच्यामुळे हे असं दाखवत नाहीये, लक्षात घ्या. But you'll see that the effective wind direction, when it develops exactly opposite to the effective wind direction, you are going to have a frictional force as such. Now you minus this frictional force in the third condition, and what happens at a particular level is that the PGF and the Coriolis force, they are equal to each other, and because of that, you'll see that the wind tends to blow parallel to the isobars. Comparison between upper air levels and surface levels showing the effects of frictional or airflow. Friction slows the surface wind speed, which weakens the Coriolis force. Okay, because you'll see that Coriolis force is directly proportional to the speed. Okay, so you'll see that if speed is more, Coriolis force is going to be more. If speed is less, Coriolis force is going to be less. Okay, who helps this? Okay, the frictional force. Okay, हे असं एकमेकाला ते जोडून घ्यायचं आहे. Okay, then on a general level, what happens? Okay, you'll see that this is the equator. These are the poles. Okay, as far as the poles and the equator are concerned, there is, of course, the you're going to have a lesser number of okay, here you will see that the pressure is higher. Here you're going to have low pressure. So if you're going to move in this particular direction, this is your pressure gradient force. The Coriolis force is acting opposite to it. When it comes opposite equal, you'll see that the gradient wind starts blowing parallel to the isobars as such. Okay, this is what the geostrophic winds we were referring to. We have gone into the details of that from point number 1 to 2 to 3 to 4 and eventually 5, where it starts moving. Okay, the same thing when it happens along a curved path, okay, you'll see that the centrifugal force and the centripetal force, okay, they are going to impact it as such. Okay, in fact, you'll see that just it's very similar to this. Okay, it's this is number two and this is number one. Number one is very similar to number two. It's only that it is along the curved path, and for this along the curved path, this diagram, for the curved path, if it has to keep along the center, then the centripetal and the centrifugal forces come into picture. And if they are going to balance it each out of the balance out each other, what is going to happen is that the uh, pressure gradient force is equal to the Coriolis force. This is one set, and which is equal to, okay, which is, I would say, balanced by the centripetal force, which is going to be equal to the centrifugal force. If all of this is equated, okay, eventually you're going to have what is going to be called as gradient wind. Got it? This is how it happens. Okay, speaking about the Coriolis force, I said that at the equator, the Coriolis force is zero. At the poles, the Coriolis force is max. Okay, and that also happens. Another issue now, this is generalized the straight, but we know that it is at an angle of 23.5 degrees. The axis is at an angle, and that's why you'll see that the deflection tends to be large near the poles and the deflection is near to zero as far as the equator is concerned. And you'll see that the deflection, longer the flow of the winds, you'll see that larger is going to be the deflection. Okay, you'll see here, this is initial stage. This is after 4 hours, the deflection is not much. After 8 hours, you'll see that the deflection has further increased as such. Okay, you can read the description which is given down here as such. Now, to understand what exactly jet streams are, I've already given you an introduction into it. Okay, we need to understand a few things. Okay, you'll see that why is flying an aeroplane so very a difficult task, or you should be very technically sound in all these things. Basically, because as far as an altimeter is concerned, what is an altimeter? It measures height or altitude, but this is based on pressure. Okay, so the pressure values are going to give you the height. Now, if the pressure falls, what would happen? Of course, it is going to be difficult to measure at what height you are, and that is why what is done is this sea level pressure. Okay, what you do is sea level 1008 MB. Now, if you are at sea level, then your pressure is this. Now, if you go to a height, मी हे आधी सुद्धा एकदा बोललेलो आहे की you don't have this amount of air pressure in that. So obviously, you'll have to subtract this from this. So what you do is you come up with a correction, and this correction is 840 MB plus the correction value. Okay, and thus the pressure here is going to be 1012 MB. Okay, and this correction is used here, and that is why you'll see that along this value, okay, we have to know that the altimeter reads 10 kilometers. तर लक्षात घ्या की हे height change झाली याची, पण along this height it is going to show 10 kilometers. So you need to know what is the pressure. If you know the pressure at that particular level, then you can correct the value as such. Okay, I've purposely put the whole box. Those who are interested, let me tell you, this is there in Lutens and Turberg, and you can go into the details of that. Remember, this is in the 6th chapter, 6.6b, 6a, and of course, this is 610. Okay, this is in the 6th chapter. You can read the whole thing. Okay, how the aeroplane tends to adjust its height according to the fact, and adjust in the sense it needs to give you the correct व्हॅल्यू ऑफ द हाईट, नाहीतर एअर क्रॅश होऊ शकतो. You'll see that in the warmer air, what happens in the warmer air, because this is light, okay, the particles are away from each other. Okay, you will have to fly higher. Okay, you are actually at 2.5 feet, 2.5 kilometers, but it is still showing you 2 kilometers. It's only when you come down here. Okay, now standard atmosphere is here. In cold air, what is going to happen? You're going to have high pressure, so your 2 kilometers is going to look here instead of here. हे थोडंसं समजून घ्यावं लागेल की ही जी 2 किलोमीटरची व्हॅल्यू आहे, ही जर वॉर्म एअर असेल तर तुम्हाला वर गेल्यावर ती 2 किलोमीटर जाणवते, आणि तीच 2 किलोमीटरची लाईन ही जी तुम्ही कोल्ड एअर मध्ये गेलात तर इट विल बी ऑब्झर्व्ड ॲट अ लोअर हाईट एज सच. सो दिस इज व्हॉट is the role that cold air and warm air plays as far as this whole issue is concerned. I'm telling you this basically because we need to understand how the jet streams are formed. I will go into understanding, making you understand the jet streams, which is here. But before that, I would actually show you a small clip which is on jet streams. त्याची I think I have pasted the, yeah, इकडे आहे, नंतर तुम्ही ती पाहू शकता. But let us for now do one thing, that I'll come here, I'll move to this, okay, and let us see what these people have to say about the jet stream. Just a moment, we are not able to hear it. I don't know why. I'll do one thing, I'll stop sharing this, stop presenting, and then I will take you to this tab, and let us do that first. Yeah, let me come here, and now let us say
different jet streams that exist. Jet streams are another name for fast-flowing currents of air. There are many different jet streams that exist at both high and low levels in the atmosphere. Each has an important role to play in the weather experienced on Earth. The major jet streams that circle the Earth are found just below the tropopause at a height ranging from 9 to 16 kilometers and can reach speeds over 200 miles per hour. They are hundreds of kilometers wide, but only a few kilometers deep, so are often described as a ribbon of very strong winds. The major jet streams are the polar front and subtropical jets. These occur in both the northern and southern hemispheres and are part of the larger global circulation. The polar front jet occurs over mid-latitudes and strongly influences the weather over the UK and Europe. The polar front jet is a type of thermal wind that arises due to the strong temperature contrast between cold polar air and warm tropical air. To explain this further, imagine two columns
this
of
is a very
air,
important explanation.
one in the cold air to the north of the jet and one in the warm air to the south. The top of each column is bounded by the tropopause. A shorter column of cold air exerts the same surface pressure as a taller column of warm air. This is because in the cold air column, the air is more dense. This causes atmospheric pressure to decrease more quickly with height. In the warm air column, pressure does not decrease as rapidly with height. because the warmer air is less dense. The tropopause in both columns is at the same atmospheric pressure. So if you were to climb to the same height in both columns, you would find that you would be at a lower atmospheric pressure in the cold air column and a higher atmospheric pressure in the warm air column. The pressure difference caused by this temperature gradient produces a pressure gradient force. The pressure gradient force acts from high to low pressure, so theoretically in the northern hemisphere, air would flow from south to north. But the Coriolis force resulting from the Earth's rotation causes the air to move to the right of the direction of motion in the northern hemisphere and to the left of the direction of motion in the southern hemisphere. In both hemispheres, the jet stream flows parallel to this temperature gradient, moving from west to east. Theoretically, this jet encircles the Earth in a continuous line, but in reality it is more broken up, as differential heating of land sea masses lead to west to east temperature contrasts as well as north to south. As the polar front jet forms due to the temperature contrast, the stronger the temperature gradient, the stronger the jet. This means that the jet is stronger in the winter than the summer as the poles cool during the winter months, increasing the temperature contrast. In the northern hemisphere, the jet tends to be further south in winter and further north in summer. This is due to the tilt of the Earth, and that in the winter, the northern hemisphere is tilted away from the sun, and in the summer it is tilted towards the sun. Mid-latitude low-pressure systems occur on the polar or northern side of the jet stream, while more settled, warmer conditions are found to the south. This gives us the wet and windy weather we often see in the UK during the winter months, as low-pressure systems are steered towards us. It can also lead to some disappointingly wet summers if the jet stream remains to the south of the UK. A stationary jet stream pattern will bring frequent low-pressure systems to the same region. When warm air moves further north than normal, or cold polar air moves further south, this can change the prevailing west to east jet stream pattern. This causes the jet stream to buckle, driving depressions towards different regions or blocking their movements altogether. A straight west-east flowing jet stream won't have much impact on the development of new weather systems or strengthen pre-existing ones. When a jet stream meanders north and south, air accelerates and decelerates around the bends in the flow. These areas of changing speeds are our development areas. Where the air is accelerating, more air is leaving than entering a certain point. This means that the air is being depleted at this point. To fill this depletion, air from below rises. When air rises, it forms clouds and precipitation. Winds at the surface converge to this rising air column, which causes surface pressure to fall, and a low-pressure system may develop or deepen further. So whilst the jet stream is just an area of fast-flowing air, it has a fundamental effect on our weather.
Sorry, that was about the jet streams. I had just switched off my mic. Um, a lot of things are very, very clear as far as this 5 minutes. Now, it actually is for 5 minutes, but I had purposely reduced the speed of the uh, rolling. So basically, to so that we could understand the English the lady was speaking. And as a consequence, it may have gone a bit more. I think it ran into 6 minutes instead of five. But then the link of that is available. Let me tell you that the operational things are very clear in this. At any point of time, you can come back to this particular thing and you can watch it. But yes, we need to do the theory of this. We'll do the basics of this theory today. We'll come back to understanding what it actually means at a larger scale tomorrow. Once again, as I do every time, we are going to do the understanding of the whole things. So we'll just confirm what the lady was saying. Okay, we'll start with diagram A here as such. These are very, very fast flowing winds. Embedded within the westerly flow aloft are narrow ribbons of high speed winds. Okay, how high? You'll see that they are. The lady was saying that the highest speeds could be as much as 200 miles. That means nearly 400 kilometers per hour. Okay, so this is very, very fast, let me tell you. And they meander. This is a word normally used in geomorphology, but then they show a same sequence, and that's why we say that the jet streams meander. And they are, how long are they? They are circumpolar. Okay, they move all along. Okay, कुठेही त्याच्यामध्ये break नसतो. That's why the word is circumpolar. Then the total length could be a few thousand kilometers as such. These fast streams of air, once considered analogous with the jets of water, were named as jet streams. Jet streams occur at the top of the troposphere. Remember that is very important. And they have their widths that vary from less than 100 kilometers to 500 kilometers. Wind speeds exceed 100 kilometers often, occasionally 400 kilometers per hour. Although the jet streams have been detected earlier, okay, they were more brought into picture in the Second World War. American bombers heading east toward Japan occupied islands sometimes encountered unusually strong headwinds. Okay, remember they were flowing from they were going from America to Japan during the Second World War, and the jet streams are coming this way. So that's why they used to come strong headwinds, obstructions. Okay, and on coming back, okay, they were along with the jet stream, so the plane experienced strong westerly tailwinds during the return of the flights as such. Okay, the altitude at which they occur. Okay, you'll see that it's at the tropopause. So wherever the tropopause is, okay, that's between 7 kilometers to 12 kilometers. You could have them. As far as the actual winds are concerned, the total depth is 1 to 3 किलोमीटर. म्हणजे त्याची जाडी जी आहे ही 1 ते 3 किलोमीटर आहे. विड्थ जे आहे त्याची, okay, विड्थ, okay, हे 1 ते 3 किलोमीटर आहे. हे 100 ते 500 किलोमीटर आहे. आणि लेंथ जी आहे ही thousands of kilometers आहे. आता you'll see that all of this does not flow at one speed. You'll see that the innermost part is flowing at the maximum because the friction is the least. Okay, as you come outside, the outer layer is in friction with all that is happening next to it, and that's why the outermost layer is very small. But very small mandala tari, it's 8 dune 16. So this is 160 kilometers, while the innermost layer at that particular point could be 280 kilometers. Okay, so there could be a gradient, a huge gradient as far as the speed also is concerned. Now, across the uh, section of the atmosphere, where are you going to expect jet streams? A cross-sectional view of the polar and subtropical jet streams. The blue ones are polar, these are subtropical jet streams. Okay, here is where you're going to have polar. Okay, you see them here, and here you are going to have the subtropical jet streams as such. Okay, these are more prominent. Okay, that is as far as the jet streams are concerned. Now, Um, as I saw, the lady was speaking about a few things, and let me bring it to your notice here also. That a comparison, sorry, there's a comparison between density. This is cool air. This is warm air. Okay, so the same amount of particles are going to be occupying at a lower level as compared to at a higher level, and this could be the normal. So during cold air, in colder airs, you could experience the height in a different way. If you remember, we're speaking about the altimeter there, and for attaining the same height, you'll have to go up a bit in a warmer section as such. Coming back to the fact that they are very, very fast flowing winds, okay, because they go very fast, what happens is at times they start meandering. When jet stream starts meandering, they are called as Rosby waves. Remember, this is a very common question asked in exams. Okay, much of our knowledge in the large scale motions is attributed to C.G. Rosby, okay, who explained the wavy pattern of these winds. Okay, and the longest wavy patterns, Rosby waves, usually consist of 4 to 6 meanders. Okay, that means in all, we could see this in this diagram number C: one wave, two wave, three wave, four wave, and five waves. They have said it is between 4 to 6. Where was it? 4 to 6 meanders. And at times, what happens? Just like you have an oxbow lake. Okay, this could have been the oxbow lake, but then in this context, this is important. So these parts are going to be colder. Okay, they are going to have an unusual climates. And similarly, if a warm air is going to introduce here, and you could have a low pressure here, okay, it could lead to warmer conditions as such. Okay, from moving from stage 1 to stage 2 to stage 3 to stage 4 and then back to this is called as indexing of the jet streams. Sorry, jet streams. Okay, now remember, there are three aspects that you have to remember. One is the normal jet stream, then the wavy jet streams are called as the Rosby waves. And from normal to Rosby and back to normal, this is called as indexing of the jet streams. And it is these diagrams that is going to show you the indexing as such. Okay, this is the first stage. The normal jet stream begins. Yeah, this is the normal jet stream. Then the Rosby waves begin to form. Okay, you'll see that the wavy things start. Then the wavy things get stronger. This is number 3, and then they leave pockets behind. Okay, this is going to be a low pressure pocket, this is going to be a high pressure pocket, and so on and so forth, alternating low high pockets as such. Okay, and what will this lead to? Okay, you'll see that in lower latitudes you could have cold, and in higher latitudes you're going to have warm. So what has happened is that it is moved like this. It's as a complete करायचा diagram म्हटलं. So this warm air is moved here, and this cold air is moved into this particular direction, just as it has been shown here as such. This is called as indexing. Indexing brings about a lot of changes. Okay, and she said that if the gradient is more, okay, the jet streams are thick. If the gradient is less, then the jet streams are thin as such. These are a few things that we have to keep in mind. And yeah, before, sorry, what's the time? Okay, I have 15 minutes with me now. We'll of course be coming back to this tomorrow as well, but yeah, remember that you may have a question that why is sir showing ocean currents as such. It's basically because of the fact that ocean currents, yes, the rotation of the water is going to push it, the Coriolis force and so on and so forth. But remember that this also has to do with global winds. These, okay, here, or let me change the color here. Okay, this is the belt of trade winds. Okay, so trade winds are east to west, east to west, east to west in the northern hemisphere and the southern hemisphere also. Okay, that is it. In this area that's around this, you're going to have the westerlies, and that is why you're going to have the water moving towards the west. Again, Coriolis force movement is in a clockwise direction in the northern hemisphere. Coriolis force movement is in a anti-clockwise. हे समजलं असेल तर ठीक आहे, समजलं नाही तर तुम्ही हे परत जेव्हा पाहाल तेव्हा 100% तुम्हाला हे कळेल. You have to imply the impact of global winds, Coriolis force, on the waters as such, and that will give you an idea as to how these move as such. Okay, so that is about the gradient winds. This is the link of the clip we have just seen. Okay, this is what. Okay, of course we'll go into it. These actually are the 4 stages here. Okay. When we meet tomorrow, we'll go into the details of that again as such. For now, what I'll do is I'll just opt out of this, and then let us come back to understand these things. Okay, now I hope you have understood the whole issue about what the jet streams are. If you have not, tomorrow first thing I'm going to do is I'm going to take up a revision on this, and let's see if we understand it tomorrow, or if we have not understood it today. For now, I'll just take your attendance. Aishwarya Limaye, Aisavari Kale, Prajakta Jadhav, Pratik Kokde, Pritam Ghosh, Revati Shinde, Rohit Ithape, Vishwikesh Aglave, Sharayu Takavane, Shreya Chavan, Sumit Nanavre, Sunil Rathod, Tushar Kothule, Usha Wasave, Mandita Bhamre are the 15 students present today. If you have any questions, you can ask me those questions. We have a few moments before we can call it a day. But yeah, if you have any questions, you can. I'm waiting for your questions as such. By the way, the jet streams do have a very prominent impact on the Indian monsoon also. I will come up with a picture tomorrow as far as the Indian monsoon is concerned, and we will see the impact of the jet streams on the Indian monsoon. In fact, it is said that the onset of the Indian monsoon is very much dependent on the jet streams. How does it happen? I'll just give you a hint. Remember, jet streams height is 7 to 12 kilometers. Okay, 7 to 12 kilometers. Now, as you go away at the equator, yes, you could say it's 15 kilometers and so on and so. But as you go away from the equator, particularly you come to 23 and a half, it's going to come down. Okay, you come to 30 degrees, you comes tropopause comes further down, and the height at which the Himalayas are. See, interestingly, just try to get the latitude of the say Mount Everest, the latitude of Mount Everest, that is going to be 8.5 kilometers, and check what is the height of the tropopause at that particular latitude if you can, and try to imagine what I am saying. Okay, that you're going to have the say the Mount Everest, and then you're going to have the jet streams which are coming. What is the impact that Mount Everest will have on the coming jet streams? You imagine that, and you may realize what is the role that that jet streams play on monsoons, or the Himalayan peaks play on the jet streams, and how does it impact the advent and the withdrawal of the monsoon as far as the jet streams and this. Of course, that's not the only connection as far as the monsoon is concerned. If you remember, the Govarikar model speaks about 16 parameters on which the monsoon is or by which the monsoon is impacted for. But this should give you an idea that the Mount Everest is protruding out, and it's not only the Mount Everest. There are so many other peaks also which are 7,000 plus. Okay, and it's going to be blocked. It's going to be blocking. All these are going to be blocking this. What happens because of that? is going to be very interesting to be seen tomorrow. But of course, we'll do the revision of jet streams tomorrow, and then we'll speak about what is the impact of the Himalayas